Hey, this is Alex from GMAT Ninja. Welcome to our GRE video on geometry. This is video 1 of 2. So the goal of today's video is to cover the following topics: special right triangles, Pythagorean theorem, triangle inequality theorem, or what you can figure out about the third side of a triangle based on the other two sides, surface area and volume of 3D shapes, and similar figures. So these are concepts that any GRE test taker is going to want to have in their geometry toolkit, and the goal of today's video, Geometry Part 1, is to apply them in fairly straightforward contexts, although it will get more complex as we move through the video. Now, if you find these questions too simple for your taste, feel free to skip ahead to Geometry Part 2, the next video in the series. That one's going to cover a lot of the same concepts, but apply them to more challenging questions. So we're going to have 8 questions total in this video. We'll give you 1 minute and 45 seconds for each one, but feel free to pause it if you need more time to solve. On the other hand, even if you get to an answer, you may still want to check out our solution. There's a lot of different ways to do any GRE question, and your goal is not just to get to an answer, but to get to it in the most efficient way possible, in a way that'll be useful for you on test day. Alright, great. Let's take a look at the first question. Alright, question number 1. Which is bigger, quantity A, the perimeter of triangle ABC, or quantity B, the perimeter of triangle PQR? Okay, well let's analyze triangle ABC first. I notice I've got a right triangle. I notice I'm told 2 out of the 3 sides. Well, if that's ever the case, I can use the Pythagorean theorem. So I square and add up the 2 legs. That's equal to the square of the hypotenuse. Okay, so in this case, I'm told the 2 legs, each of those is 3. So that gives me 18 for c squared. C is equal to the square root of 18. Root 18 is equal to 3 root 2. Okay, so I found the hypotenuse. I can now find the perimeter. I combine the like terms, adding up all the sides. I get 6 plus 3 root 2. So there's the perimeter of triangle ABC. Now, if any of those calculations were at all confusing, involving the roots and simplifying and all of that, feel free to check out our exponents and roots video. But I'll push ahead here. So is there any more efficient way to do this question? Well, it turns out if I spot the fact that I'm dealing with a special right triangle, I can do this question a lot more efficiently. So how do I know that I have a special right triangle? Well, it's a right triangle that's isosceles. Those 2 sides are the same. That tells me these 2 angles have to be the same. Now, all the angles in a triangle have to add up to 180, so these 2 angles have to be 45 degrees. Okay, so that tells me I've got a 45, 45, 90 triangle. Now, if that's the case, I can always apply this formula that relates the lengths of the 3 sides. X root 2. X root 2 is the length of the hypotenuse. Both of the legs are equal to x. So notice, as long as I know one of the 3 sides, I can find the other two really easily. In this case, I know that one of the legs, or x, is equal to 3, so then I can find the hypotenuse is 3 root 2. So that gets me to the length of the hypotenuse in a much more efficient way than using the Pythagorean theorem. So if I'm ever dealing with a 45-90 triangle, I want to spot it immediately, and this formula should come to mind because it can probably make my life a lot easier. Okay, let's proceed to triangle PQR. Well, I want to find the perimeter. I'm told that it's a right triangle, but I only know one of the three sides. So I can't use the Pythagorean theorem here. For that to work, I'd need to know 2 out of the 3 sides. So what can I do? Well, the key is to recognize that you have another special right triangle here. I have a 30-degree angle, I've got a 90-degree angle. So to add up to 180, this one has got to be 60. So that reveals, okay, I've got a 30, 60, 90 triangle. And there is, in fact, a formula for this as well. The side lengths have to be in the following ratio, x to x root 3 to 2x. Now, notice these are going from small to large, just the way the sides of the triangle are. So that's how I can figure out which side corresponds to which of these elements in the formula here. The smallest side of the triangle is x, the middle one x root 3, the hypotenuse 2x. Okay, so it would appear that I'm given the smallest side, but how can I confirm that, right? I don't want to assume just because they drew it as the shortest side that it is. You know, the drawings are not necessarily to scale. Well, the smallest side of a triangle is opposite the smallest angle. Biggest side opposite the biggest angle. So the smallest angle here is 30 degrees. That confirms, yes, 2 is in fact the smallest side. That means that x is 2 in this formula. So the middle side, the one opposite the 60, is 2 root 3, and the hypotenuse is 4. So I've got all 3 sides. I can add those up. I get 6 plus 2 root 3. Okay, so now the question is, which of those two is bigger? Well, they both have a 6, so essentially I'm just comparing 3 root 2 and 2 root 3. So at that point, sure, I could punch those into the calculator. That's really not too bad. On the other hand, it could be nice to be able to approximate these square roots. So here is a list of some common square roots that it's nice to be able to approximate. It can make your life easier in some circumstances. So the square root of 2 is about 1.4, square root 3 about 1.7, root 10 about 3.1. Now, there's a mnemonic to help you remember these decimals. 2, 1.4, well, that's kind of like 214, which is Valentine's Day, February 14th. 3, 1.7, kind of like March 17th, or St. Patrick's Day. 10, 3.1, well, that's kind of like 10/31, Halloween. So having these at your fingertips can be nice if you ever want to do a decimal approximation. So root 2 is about 1.4, so this is about 4.2. This is about 2 times 1.7, so 3.4. Okay, so that confirms 3 root 2 is bigger than 2 root 3, so the perimeter of triangle ABC is bigger. So the final answer to this question is A. Okay, so any take-homes? Basically, if you see a special right triangle, you want to make sure you apply those formulas. You know, for 45, 45, 90s, it's x, x, x root 2. If it's a 30, 60, 90, it's x, x root 3, and 2x. So if they show up, you want to spot them, you want to make use of these formulas. On the other hand, just because you have a right triangle that kind of looks like one of these triangles, you don't want to impose the formula unless you're 100% sure that it's going to fit. So you'd want to prove to yourself, yes, I do in fact have a 30 and a 60 degree angle, or I do in fact have two 45 degree angles. And if that's the case, go ahead and use those formulas, and that should help a lot. Okay, great. Let's check out the next question. Okay, another quantitative comparison question here. R is a regular octagon. So which is bigger? Quantity A, the degree measure of one internal angle of R, or quantity B, 135. Okay, so let's sketch what we have here, a regular octagon. Okay, so that's an 8-sided shape. It's going to look something like a stop sign. It's regular, so that means all of these sides have the same length, and also all the angles have the same measure. So it's a totally symmetrical shape. And these polygons in general and regular polygons in particular are popular, show up with some frequency on the GRE. So it's good to know some formulas that apply to polygons in general and specifically to regular polygons. So we'll discuss those. We'll talk for a minute about why they make sense, and then we'll apply them to this question. So first let's talk about, there's a formula for the sum of all the internal angles in any polygon. So sum of all internal angles in any polygon. So notice it doesn't need to be a regular polygon for this formula to apply. In other words, all the sides, all the angles don't need to be the same. Though they can be different, I would still be able to apply this formula. 180 times n minus 2, where n is the number of sides. Okay, so that could tell me the sum of all the angles, but this question is asking about one particular internal angle. So there's a different formula for that. So let's say the internal angle of a regular polygon. Okay, now, well, the sum of all the angles will just be 180 times n minus 2. We already have that formula down. And then notice if there are n sides, that also means there are n angles. So if I divide by n, that'll give me the number of degrees in any one of those specific angles. Okay, so again, polygons, regular polygons, show up with some frequency on this test. So these are two formulas I definitely would want to have at my fingertips. Now, we can think for a second about why these formulas make sense. Well, we'll draw some polygons here. I'll draw, say, a triangle. That's a common polygon. I'll draw a 4-sided shape. I'll draw a 5-sided one. Well, we already know that there are 180 degrees in a triangle, right? And it's also good to know there's 360 degrees in any 4-sided figure. So notice as I go from 3 sides to 4 sides, I'm adding 180 degrees. And that's what gives you the 180 in this formula. Every time you add another side, I get another 180 degrees. Okay, and if I test this formula out, well, if I have a 3-sided shape, in other words, a triangle, I plug in 3 here, that gives me 180. And then as I keep adding more and more sides, I keep getting more 180 degrees. Kind of makes sense because a 4-sided figure is really just 2 triangles stuck together, right? Or you could say a 5-sided figure is really just 3 triangles stuck together, and so on. Okay, so once I know this formula, I'm in good shape for this question. There's not too much more to do besides apply it, find the value, and compare. So it's an octagon. That means that the number of sides is 8, so n is 8. So I'll do 180 times 8 minus 2 over 8. Okay, now I can simplify this. So 6 over 8 is just 3 over 4. Now, I prefer to make numbers smaller than to make them bigger, so I'm going to divide by 4 first, then multiply by 3. So 180 over 4, well, 180 over 2 is 90, divide by 2 again is 45, so I get 45 times 3, and that gives me 135. Okay, so one of these internal angles is equal to 135 degrees, so A and B, those are equal, so the correct answer to this question is C. Okay, so the take home for this one is, well, polygons show up with some frequency, so you want to know these formulas. Keep in mind, this one only applies to regular polygons. It gives you each of those internal angles. This one, on the other hand, will tell you the sum of the angles for any polygon you encounter. Okay, great. Let's take a look at the next question. Okay. If the isosceles triangle PQR has at least one side with a length of 7 inches, which of the following could be the perimeter of PQR in inches, indicate all such values, and then I'm given a bunch of options here. So any of these that could fit as the perimeter, I want to select those for my answer. Okay, well, let's start thinking about the information we're given. An isosceles triangle, so that means the measure or the length of two of the sides is the same. So I'll draw an isosceles triangle. Now they don't tell me which two sides are the same, so I'll just arbitrarily write PQR in that order. They also don't tell me, if I'm considering the case where one of the sides is 7, which of the sides it would be, so I'll just arbitrarily say, let's consider PQ is 7. Okay, notice these two sides are the same the way I've drawn my isosceles triangle, so I've got two 7s, and then I don't know the third side. Okay, so I could explore this further, but I might want to ask, is this the only possible, triangle I could have with at least one side length 7? Well, what if PR was the side with a length of 7, right? I arbitrarily picked PQ, but what if I picked PR? Well, then I wouldn't know anything right off the bat about PQ and QR, so I'll just call those X. Might be worth considering, well, what if I started with QR as 7? Well, that would lead me just back to this triangle here. Okay, so I'm considering all the relevant cases. Now I can consider these further, see what the possible perimeters are. Now to do that, I'm going to want to think about applying the triangle inequality theorem, otherwise known as the hinge theorem, and let's consider a case of that first. We can think about how it works, and then we can apply it to these particular cases. Okay, so I'll just draw a triangle with sides of length, let's just say 3 and 5, and I'll leave the third side unknown. So based on these two sides, what can I conclude about x? What are the range of possible values of x? Well, let's consider what's the biggest possible value x could have. Well, for x to get bigger, I suppose that would mean this angle is getting bigger. So as the angle between those gets bigger, you can see on the drawing, yeah, that does in fact make x longer. So the bigger the angle gets, the bigger x gets. What's the upper limit on x? Well, notice if I stretch 3 and 5 out so that that angle is 180 degrees, that gives me the maximum length of that third side of the triangle. In fact, I don't even have a triangle at that point. It's so spread out. So that third side is always going to have to be less than 8. Okay, so that tells me the third side of a triangle always has to be less than the sum of the other two sides. Because when you stretch the angle out as wide as it possibly can, and then you sum those two sides, that gives you the upper limit on the third side. Okay, now what's the lower limit of x? Is there some small value that it can never reach? Well, notice as the angle gets smaller and smaller, as the 3 and 5 get closer and closer together, yeah, that side x gets smaller and smaller. So what's the lower limit? Well, if 3 and 5 are sitting right on top of each other, right, then the distance between the ends of those two lines would be the difference between 5 and 3, right? It would be 2, and you could never have a triangle at that point because everything's just lying on the same line. So the third side needs to be greater than the difference between the other two sides. Okay, so this is a formula. It applies to every triangle, and you can consider any of the sides, and what you can conclude is any particular side has to be less than the sum of the other two and greater than the difference. Okay, so let's apply that to one of our examples here. And the third side that we're interested in is the unknown x. Okay, so x needs to be less than the sum of the other two sides. So x has to be less than the sum of 7 and 7. And it needs to be greater than the difference between 7 and 7. Okay, so that tells me the range of possible values of x, it's got to be less than 14, greater than 0. So what does that tell me about the perimeters? Well, the upper limit on the perimeter would have to be 14 plus 7 plus 7, so it's got to be less than 28. And on the other hand, that p has got to be greater than 7 plus 7 plus 0, so greater than 14. Okay, so I've got a range of possible perimeters. Let's do this one, and then we'll be ready to look at the answer choices. Okay, so I'll apply the same logic. This side here, 7, has to be less than the sum of the other two sides, less than 2x. and greater than their difference. Okay, I'll simplify that, and that tells me 7 has to be, or rather I'll divide by 2, I get x has to be greater than 7 over 2, which of course is greater than 0 over 2. Okay, so notice this one is less restrictive. In this triangle here, all that has to be true about x is that it has to be greater than 7 over 2, but there's no upper limit, which kind of makes sense. I could imagine drawing really, really long sides here, right? I can just make them as big as I want, but they can never be less than 7 over 2. Okay, so if the lower limits there are 7 over 2 and 7 over 2, then the lower limit on the perimeter would be, add all those up, I get 14. So x has to be greater than 14. Pardon me. The perimeter, P, has to be greater than 14. Okay, so range of possible values for one situation, range of possible values for another. Okay, so is 10 possible? Well, P has to be greater than 14, so no. Is 14 possible? Right, well, for both of these, P has to be greater than 14. Is 18 possible? Yeah, that's okay according to both of these. 18 is in range. 22, same thing. 26, same thing. What about 30? Well, 30 is out of range for this one, but it is possible for this one. So where does that leave us? Well, the question is saying, which of these is a possible perimeter given these constraints? Well, it doesn't matter. Sure, I couldn't get a perimeter of 30 with this triangle, but I could get it with this. So the constraints can lead to a perimeter of 30. In fact, the perimeter could be anything bigger than 14. So I'll take 30 as well. So that leads me to the correct answer for this question, C, D, E, and F. Okay. So any take-homes for this question? Well, this idea that the third side of the triangle has to be less than the sum of the other two, but greater than their difference, that comes up a lot on the GRE. So it's really nice to know that formula so you can apply it and create an inequality. It's also nice to understand the logic of it and to think about, well, why do you have to impose these limits on the third side of a triangle? And that can come in handy in kind of understanding the logic of this and tackling this in more difficult questions. Okay, great. Let's take a look at the next one. Okay, quantitative comparison question here. ABCD is a parallelogram. Which is bigger, quantity A, 96, or quantity B, the area of region ABCD, in other words, the area of that parallelogram? Okay, what am I told about the parallelogram? Well, one side is 12, another side is 8, one of the angles is 130 degrees. Okay, so I want to find something about the area of this parallelogram. So we need to know the area formula, which is base times height, but I also need to know how to find the base and the height of a parallelogram. So the base, let's say, is just any old side. I could pick any side. I'll just pick the bottom for simplicity. Okay, now the height is going to be the distance between the base and the side opposite. So to find that, I'll draw a line that makes a 90-degree angle with both the base and the side opposite the base. And then the length of that line that I drew will be the height. Now, notice the height is not equal to one of the side lengths. I had to go ahead and draw my own height to identify that. So let's do that on our diagram. I'll draw a line that forms a 90-degree angle between both the base and the side opposite the base. And I'll call that the height. Okay, so in this parallelogram, what's the area of region ABCD? Well, it would be 12 times that height. And that would give me the area. Okay. So let's explore that shape a little bit further. I notice I've got a right triangle there. So if I could find H, one side of that right triangle, I could find the area of my parallelogram. So let's see if that's possible. Okay, hypotenuse is 8. I've got a right angle. This is H. Anything else I know about this triangle? Okay, well, this big angle is 130 degrees. This small angle is 90. So that leaves me 40 left for this angle here. Okay, that leaves me 50 for this angle. Okay, I think that's all the information I have about that shape, that triangle. Can I figure out H from that? Well, I can't use the Pythagorean theorem because I only know one of the three sides. I'd need to know two to identify, to use a Pythagorean theorem to solve for a side. That won't work. It's not a special right triangle, right? It's not a 45, 45, 90. I don't want to impose that formula. It's not a 30, 60, 90. So if I'm focused on solving for a value of H, I hit a brick wall. So can I look at this question from another angle? Well, I don't need to find the area of the region to decide which is bigger, A or B, as long as I can find a range of possible values. Okay, well, here's a question. What would H need to be for the area of this parallelogram to be 96? Well, H would need to be 8. Okay, so let's continue that line of reasoning. Could H be 8? Well, here's a right triangle with a hypotenuse of 8. I know that the hypotenuse is the longest side of a triangle. So that means the leg, well, both of these legs have to be less than 8. So H has to be less than 8. Okay, so in fact, H can't be 8. H has to be less than 8. So if the area is 12 times H and H is less than 8, then the area has to be less than 96. Right? 12 times something less than 8 is going to be less than 96. So the area of region ABCD, the area of that parallelogram, is less than 96, so column A has to be bigger. Okay, so any take-homes from that question? Well, you really want to know how to find the area of a parallelogram, base times height, but specifically the height is going to be the distance between the base and the side opposite, and a lot of times you're going to have to draw in that height yourself. On top of that, watch out for getting rigid on quantitative comparison questions. When I was rigidly focused on finding a value for H, I hit a brick wall. There's really no way I can do it. Those angles don't help me. Pythagorean theorem doesn't help me. So how do I get around the brick wall? Well, I look at the question from another angle. I start asking myself, okay, what are the possible values that the area could be? What are the limitations on the value of H? Once I start thinking from that angle, it cracks open the question. I know H has to be less than 8, area less than 96, and again, that leads us to our correct answer of A. Okay, great. Let's take a look at the next question. All right, got a quantitative comparison question here. The surface area of cube R is 54 square inches. The diameter of cylinder S is 6 inches and its height is 1 inch. Which is bigger, quantity A, the volume of cube R, or quantity B, the volume of cylinder S? All right, well, I want to find the volume of cube R. I'm told its surface area. So let's think about our surface area volume formulas. And we'll start with a rectangular solid, and then we can apply that to the more specific case of a cube. So in this rectangular solid, we can say, let's label the sides. So I've got length, I've got width, I've got height. Okay, now the surface area is just the area of all these different surfaces, or all the different faces of this rectangular solid. So let's start with maybe the front face here. Okay, so what's the area of this rectangle? Well, notice width times height gives me the area of that rectangle. So that gets me started. Now, this rectangular solid also has a back face, right? A front face and a back face, both with dimensions width times height. So I need 2 HW to capture both of those rectangles. Okay, what about the sides? So this rectangle here, notice length by height are the dimensions of that rectangle, and I've got 2 of them on the left and the right. So I've got L times H, but 2 of them, so 2LH. Okay, what am I missing? Well, the top and the bottom. So those are going to have dimensions width times length. They both have the same dimensions. So L times W, but I've got 2 of them. So surface area for this rectangular solid is right here. 2HW plus 2LH plus 2LW. Okay, what about the volume? Well, the volume of a rectangular solid, we'll start with a formula, but we can talk about why it makes sense. So it's length times width times height. Now notice length times width gives me the area of that rectangle on the bottom. And then if I stack up all those rectangles, I'll make a rectangular solid. So how many do I need to stack up? Well, if I multiply by h, that should do the trick. That gives me the volume. Okay, what about a cube? So a cube is basically just a rectangular solid where all of the sides have the same length. So notice that each of the faces of this cube is going to be a square. We'll call each of the sides length S. Okay, so we'll start with the surface area. Notice the area of one of these squares is just S squared. And how many squares are there total on this cube? Well, front, back, top, bottom, side, side, so 6 total. So the surface area of this cube is 6S squared. Okay, what about the volume? Well, let's start with the formula again. It's S cubed, but why does that make sense? Well, the base of this cube has an area of S squared. That gives me the area of that square. If I stack up a whole bunch of those squares, I'm going to make a cube. So S squared base times height, which is just S again, gives me S cubed. Now, notice both of these formulas for cubes are just extensions of these formulas right here, right? If length, width, and height are all equal to S, this just becomes 2S squared plus 2S squared plus 2S squared, or 6S squared. If length, width, and height are S, L times W times H just becomes S cubed. Okay, so this question is about cubes. So let's use these formulas over here on the right to see what we can solve. So I'm asked for the volume, so I want to find the side length. I'm told the surface area is 6S squared. Okay, so 6S squared is 54, so I should be able to solve for S. Divide both sides by 6, I get S squared equals 9, I get S equals 3, I get S cubed for the volume, so the volume of this cube is 27. 27 inches cubed. Okay, now let's consider the cylinder. So what exactly is a cylinder? So you could think of it as a soup can. It's a circle on bottom, circle on top, and then those two are connected by a height. So let's start with the volume of a cylinder. Okay, well, a cylinder, if I'm interested in those circles, I know each one has a radius. It's going to be the same radius on the top and the bottom. And there's a height. So the distance between the two circles is your height. Okay, so how do I get the volume? Well, the formula is pi r squared times h. Now, why does that make sense? Well, pi r squared is the volume, the area of this circle down here. And if I stack up a whole bunch of those circles along this height, that'll give me the cylinder. So pi r squared, the area of the base, times the height. That's the volume of the cylinder. Okay, what about the surface area? Well, the surface area is just the area of all the different surfaces added up. So let's start with the easy ones. I know that the top is a circle with an area of pi r squared. Same thing with the bottom. So I've got two circles, pi r squared. Okay, how do I get the area going around? So if you're thinking of this as a soup can, that area going around is like the area of the label. So if you peel a label off a soup can, what are you left with? A rectangle, right? That could then be, again, wrapped around or taken off. So to find the area of a rectangle, I want to find, the length and the width. So what is this length right here? Well, notice I took it off the can, so it's going to be equal to 2 pi r. In other words, the circumference of that circle is equal to that length. From top to bottom is just the height of the cylinder. So there's my formula, 2 pi rh plus 2 pi r squared. That's the surface area of a cylinder. So this question, we actually just need the volume, but you'll encounter questions later on in this problem set and possibly on your GRE that will require you to use the surface area formula, so that could also potentially be useful. Okay, so volume of cylinder S. What am I told about cylinder S? Well, the diameter is 6 and the height is 1. Okay, I'll get those on my diagram. This height right here is equal to 1. Now I'm going to read carefully and say, okay, I want the radius, but they give me the diameter. So I'm not going to confuse those two quantities. I'm going to keep in mind that it's the diameter that's 6, so that leaves me with a radius of just 3. Okay, pi r squared h, so that's pi times 3 squared times 1, so that's 9 pi. Okay, so which is bigger, 27 or 9 pi? Well, I know that pi is a little bit bigger than 3, and I know that 9 times 3 is equal to 27. So 9 times something a little bit bigger than 3 should be bigger than 27. So that confirms, okay, B is the correct answer. Okay, so what are the take-homes from this question? Well, you could see 3D shapes on your GRE, so these formulas can come in handy, and it's good not just to have them memorized, but to understand the logic behind them. In fact, if you know the logic of how to find surface area, you don't need to clutter your mind with formulas. You can just figure out, okay, this is the logic, this is how I arrive at the surface area. On the other hand, you might encounter more complex questions where the underlying logic can be really helpful to solve those. Okay, anything else about this question? Basically just be careful with your calculations. Make sure you're reading carefully, not confusing terms like radius and diameter. And then when it comes to calculating, notice estimation can be really helpful here, right? I don't want to forget about the pi. And then when I'm comparing these two numbers, well, I don't necessarily need to crunch the numbers as long as I know that pi is a little bit bigger than 3. I know that this quantity here, the volume of cylinder S, needs to be a little bit bigger than 27. And again, that leads me to the correct answer for this one of B. Okay, great. Let's take a look at the next question. All right, I've got a multiple choice question here. In the diagram above, the line BE is parallel to line CD. AB has length 4 and BC has length 8. If the area of triangle ABE is 10, what is the area of triangle ACD? Okay, well, let's start by getting the info on the diagram. So BE is parallel to CD. Okay, I'll mark those. And let's think about what does parallel lines tell us. So I'll draw two parallel lines here and a transversal, so a line that hits both of them. Notice I'm creating some angles between the transversal and the parallel lines. So if I call this angle X, well, notice when that transversal hits the second parallel line, we're creating the same angle. Okay, and that happens a whole bunch more times. If I think about vertical angles, I know this is also an X. Okay, this is also an X. But again, the same logic applies just to confirm that those are both X. I'm creating an angle between the transversal and the parallel line, and then it gets repeated again down there. Okay, so let's think about the parallel lines on our diagram, and if there are any transversals, and what that tells us about the angles. Well, AD is a transversal, right? It's a line that hits both parallel lines. So I'll call this angle between the transversal and the first parallel line X. Notice when I hit the other parallel line, I create that same angle again. Okay, AC, also a transversal, a line that hits both the parallel lines. So if I make, let's call it angle Y right here, between the transversal and the first parallel line, I create the same angle again up here. All right, so great, we see these triangles share some angles. Let's just get everything else down before we proceed. So AB is equal to 4, BC is equal to 8. Okay, and the area of triangle ABE is 10. Okay, so we're trying to figure out the area of triangle ACD. So here's a question. I mean, the formula 1/2 base times height comes to mind. So how close am I to having a base height pair for that large triangle? And here's a more specific question. CD, if I knew that, right, could I say, okay, I've got a base height pair with CD and AC? Well, notice that's actually not the case, right? Because I can't assume that angle Y is 90 degrees. So yeah, in a right triangle, those two legs do form a base height pair. So if you know the two legs, you can get the area of that triangle. But not the case here. I don't know that angle Y is 90 degrees. So just to demonstrate that, if you don't have a right triangle, think about two sides. Yeah, this side and that are not a base height pair. Notice the height would be somewhere right there. Okay, so 1/2 base times height comes to mind when I'm thinking about calculating areas, but I don't see an easy path to getting the base and height for this large triangle ACD. Sure, I know one side, but even if I figured out the other side, that's not a base height pair. Okay, so where does my mind go from there? That formula is not going to be that helpful. Well, I noticed that the small triangle, I know its area, so that in theory should help us somehow. And the small triangle and the large triangle share two angles. So what's that situation called? That's similar triangles. Okay, so let's explore the idea of similar triangles a little more and see if it will help us with this question. Okay, so imagine a small triangle and a big triangle that share two angles. So I'll just call them X and Y. Okay, so one point, well, if these two triangles share X and Y, all the angles in a triangle have to add up to 180, so they really have to share all three sides, all three angles. So as soon as two triangles share two angles, that means they share all three angles, and it's easy to see how that creates a similar triangle situation. In other words, this bigger triangle is just a blown up version of the smaller triangle. Okay, so how can we use that to figure out more stuff about these triangles? Well, let's say we know the side lengths of this first triangle, and the second triangle we know one of the three. So could I figure out P and Q just based on this information? Well, notice this larger triangle, if I compare the sides opposite Y, the larger triangle is twice the length of the smaller triangle. Okay, and because this whole triangle is just a blown up version, well, that tells me all the side lengths have to be twice. The side lengths of the larger triangle have to be twice the side lengths of the smaller triangle. Okay, so what is P? Well, the angle opposite, the side opposite x is 5 in the smaller one, so it's got to be 10 in the bigger one. Okay, the side opposite z is 10 in the smaller one, so it's got to be 20 in the larger one. So q has got to be 20. Okay, so how can I summarize that information in a ratio? Well, let's say what we know is that the side length of the big triangle to the side length of the small triangle is equal to 2 to 1 in this situation. Okay, so that's great, but this question is asking us about the areas of triangles. Okay, so can I use this ratio of side lengths to figure out something about the ratio of the areas? Well, let's consider the base height formula again. I'll draw some heights in here for these two triangles. And let's say the height of the smaller one is 2. So what would the height be of the larger one? Well, notice the side lengths of the larger triangle are all twice the side lengths of the smaller one, so the height also has to be twice the smaller one, so it's got to be 4. Okay, so let's calculate the area of the smaller triangle, 1/2 base times height. I get the area is 10. For this one, 1/2 base times height, well, remember that the base we said is 20. So 1/2 base times height is 40. Okay, interesting. So the side lengths are in a ratio of 2 to 1, but the areas are in a ratio of 4 to 1. And does that make sense? Well, remember that the area is 1/2 base times height. And we know that the base of the larger one is twice the base of the smaller one. The height of the larger one is twice the height of the smaller one. So you're doubling the area twice, and you end up with an area that's 4 times the original. Okay, so can I go from this fact that the side length of the big triangle to the small triangle is 2 to 1, can I go directly from that to the ratio of the areas? Area big to area small. So in fact, what you want to do is square this ratio to get the ratio of the areas. Okay, and again, the reason for that is, well, the area is made up of the base times the height. If I double the base and the height, whatever I'm doing to the side lengths is happening twice when I calculate the areas. Okay, so I'll just write that down again right here in a simpler form. So the side length of the big triangle to the small triangle, if you square that, you get the ratio of the area of the big triangle to the area of the small triangle. Okay, so that should get us going on this question. But let's explore another scenario, which is, what if you had 3D shapes? Okay, now, sure, 3D shapes are less common on the GRE, I'd say, than triangles, but this could still potentially show up, so let's extend this logic just a little further. So I'll draw a small cube that has sides of length 1, so every side there is length 1, and then I'll draw one with side lengths that are twice that. In other words, each side length is 2 for this larger cube. Okay, so the ratio of the side lengths is 2 to 1. So the question is, what's the ratio of the volumes? Well, let's calculate the volumes. So the smaller cube has a volume of 1, the larger cube has a volume of 8. Okay, so notice in this instance, the volume is 8 times the volume of the large cube, I'll just call this volume of the big one, is 8 times the volume of the small one. Okay, so the question is, how do I get from the ratio of the side lengths to the ratio of the volumes? Well, you square that ratio to get the ratio of the areas. We want to cube it to get the ratio of the volumes. So if I cube 2 to 1, that gives me the ratio of the volumes, in other words, 8 to 1. Okay, and does that make sense? Well, keep in mind the volume formula is side cubed. That's how we got a volume of 8. So if each of those sides is doubled, and you multiply the sides together 3 times, well, 2 times 2 times 2 gets multiplied overall by 8. So whatever that ratio is of the side lengths, you cube it to get the ratio of the volumes. Okay, so let's proceed and apply this logic to this question. Now, because this question is about areas, not about volumes, I'm going to stick with this formula here. So, and again, that formula is the ratio of the side lengths, whatever that is. If you square it, you get the ratio of the areas. Okay. So my question would be, well, what is the ratio of the side lengths? Okay, well, what two triangles are we dealing with? ABE and ACD. Okay, so let's pick two corresponding sides. All right, so what might a side be that I'm interested in for the smaller triangle? Well, how about the side opposite x? So AB. Okay, so the side of the small triangle, let's say, is 4. What's the corresponding side for the big triangle, right? And careful here, you don't want to jump to conclusions. Is that 8? No, right? 8 is not the side length of a triangle. That's the side of some trapezoid type shape. Okay, but what about the big triangle? Well, that's AC, this whole distance, so that's 12. Okay, so I'll just reduce that. 12 to 4, that's the ratio of the side of a big triangle to a side of the small triangle. 12 to 4 is just 3 to 1. Okay, the formula tells me if I square that ratio, the ratio of the side of a big triangle to the small triangle, that'll give me the ratio of their areas. Okay, and if I square 3 to 1, I get 9 to 1. Okay, great. So that's the ratio of their areas. Now I know the area of the small triangle, right? They told me that was 10. So the area of the big triangle has to be 9 times that, or 90. So the area of the big triangle is 90. So that leads me to answer choice E. Okay. So any take-homes for that question? Well, first, don't jump into a problem and assume you have a 90-degree angle if you can't prove it, right? Here we don't, so that dictates, what rules can we apply to these triangles. Now, another interesting bit of information is, if you have parallel lines in a triangle, notice you're going to create a situation where you have a bunch of shared angles. In this case, it creates similar triangles. And when you have similar triangles, you want to think about what's the ratio of their side lengths. A lot of problems that'll get you pretty good distance. In this question, we also wanted to figure out, okay, if I know the ratio of the side lengths, what's the ratio of the areas? And this is a handy tool to have in your kit. If I know the ratio of the side lengths, well, go ahead and square that, you get the ratio of their areas. So that's what we did, and that led us to find that the big triangle has an area of 90, which gave us the correct answer for this question, E. All right, great. Let's take a look at the next one. Okay, another multiple choice question here. A right circular cylinder has a height of 6 inches and a volume of 450 pi cubic inches. Which of the following is closest to the surface area of the cylinder in square inches? Okay, so let's draw a cylinder and think about what are the relevant formulas. Well, this question is asking for the surface area and it gives me the volume. So let's review those. We covered them in a previous problem, but again, just to review, I'll call the radius of the circle there R, I'll call the height H. The cylinder is made up of two circles, and then they're separated by the height. So the volume is the area of the base, so the area of that circle, pi r squared. And then I'm going to stack up a bunch of circles. You could think of it that way. Well, how many circles am I stacking up? Well, the height will tell me that. So pi r squared times h kind of makes sense. The area of the base of this shape times the height. That gives me the volume. Okay, what about the surface area? Well, let's start with the easy part. The surface area is the total area of the outside of the shape. I know I've got a circle on the bottom and a circle on the top. So I've got two circles with radius r, so that's 2 times pi r squared. But there's also the area going around the cylinder. That's sometimes called the lateral surface area. Well, how do I get that area? And if you think of it as kind of a label on a soup can, if you peel it off, the shape you'd be left with would be a rectangle. Okay, and if we think of that as the length of the rectangle, let's say, how long is that? Well, it's whatever the circumference of that circle is. So in this case, the length of this rectangle is 2 pi r. That part of the label is just the height of the cylinder. So if we want to get that area, it's 2 pi r times h. Okay, and that gives me the surface area, or in other words, the area of the outside of that cylinder. Okay, so let's see if these formulas will help us calculate what we want here. So we're told that the height is equal to 6. Okay, so that's up and down, that's 6. And we're not told the radius directly, but we are told that the volume is 450 pi. Okay, so 450 pi is equal to pi r squared h. Now, to find the surface area, I need the height. I've already got that. I need the radius. Okay, if I solve this equation, I'll get the radius. So let's do that. Okay, so I'll first cancel the pi on both sides. 450 r squared h. I'm told that the height is 6. Okay, so I can substitute 6 in for the height. Divide both sides by 6. Okay, so 450 divided by 3 is 150. So divide that in half, because I'm really dividing by 6. So I get 75 is equal to r squared. Okay, and then r is equal to the square root of 75. So root 75. 75 has a 25 in it, right? 25 times 3. So root 25 is 5. I'm left with root 3. Okay, so the radius is 5 root 3. So to get the surface area, I need to do 2 pi r squared. Okay, so I'm going to write this all out and just take my time with each of the calculations so I don't make a careless error. So the radius is 5 root 3, so that's squared, plus 2 pi, the r is 5 root 3, times the height, which is 6. Okay. So what's next? Well, 5 root 3, well, I just kind of worked with that, right? I got the square root of 75 is 5 root 3. If I go the other way, it should give me 75, right? 5 squared is 25. Root 3 squared is 3, so 25 times 3 is 75. So 2 pi times 75, otherwise known as 150 pi. Over here, okay, let's see. I'll just multiply all the integers together first. 6 times 5 is 30. 30 times 2 is 60. So I've got 60 times root 3 times pi. Okay, so root 3 could fall back on the calculator, but you might remember from an earlier problem we talked about some estimates of square roots can be handy. Root 3 is about 1.7. Okay, so 60 times 1.7, well, 60 times 1 is 60. 60 times 0.7 is about like 42, right? Because 6 times 7 is 42, so 60 times 0.7. So that gives me a total of about 102, okay? I add those together, I get 252 pi. Okay, and this isn't exact, that's an approximation, right? I rounded root 3, but on the other hand, this is asking which of the following is closest. Okay, so I don't need an exact number as long as I have something that's close. How much can I round? Well, notice these answers are pretty far apart, 800, 640, 560. So we're not drawing a super fine distinction, right? As long as it's within, 100 of the right answer, we should be in good shape. Okay, 252 times pi, well, pi is 3.14, so 252 times something a little bit bigger than 3, so that's roughly 250 times 3, which is something bigger than 750. Okay, so once I've made that estimation, all of these four answers are out, right? The only possible answer at that point, if I'm bigger than 750, is 800. Pretty close to 750, so 800 seems like a good estimate. Okay, so what's this question all about? Well, basically, know these formulas. They can come in very handy. It's also nice to understand the logic behind them. How do you get to the surface area formula? It makes it easier to remember. You don't crowd your mind with as much memorization. But on top of that, be really careful with your calculations. Don't drop your pi, right? If I forgot about my pi, maybe I would have picked answer choice A. Be careful with your square roots. Check your work along the way. If you do all that, you get to an answer something bigger than 750, which leads us to the correct answer of E on this question. Okay, great. Let's take a look at the next one. Okay, got a quantitative comparison question here. Figure 1 shows a circle inscribed in a larger square. Figure 2 shows a small square inscribed in a larger square. The larger squares in Figure 1 and Figure 2 are identical, and both have side lengths of 12 inches. Which is bigger, quantity A, the area of the circle in Figure 1, or quantity B, the area of the smaller square in Figure 2? Okay, so I'm comparing the shaded area, this circle, or this shaded area, the smaller square. Okay, well, the formula for the area of a circle is pi r squared, so if I were to figure out the radius of that circle, I'd be in good shape. They don't tell me the radius directly, but if I think about this circle being lodged into that square, well, notice if I draw a line from where the circle is touching the square on top to where it's touching on the bottom, okay, that's just going to have to cut right through the center of the circle, and it's going to be the side length of the square is going to be equal to the length of that line I just drew, which is otherwise known as the diameter, right? A line that goes across the circle cuts through the middle. So that has to have a length of 12. Cut that in half. I know that the radius is 6. Okay, so if r is 6, I can calculate the area, 36 pi. Okay, now what about this square? Well, how could I find the area of a square? Well, one thing that comes to mind is if I could find the length of one side up there, well, I'd know that's the length of all the sides because it's a square, and so side squared would give me the area of the square as a whole. Another option that comes to mind is, well, when I want a shaded area, I can take the area of the large figure and then subtract the unshaded areas, so the area of each of those triangles, and then that'll give me what's left over, the shaded area. Okay, so two potential paths there. So do I know anything about the length of the side of the square? Well, I guess to figure that out, what would I want to know? Well, if I knew this length right here, for instance, or maybe this length up here, in other words, if I knew, two legs of these triangles, I could use that to calculate a side length, right? And why do I say that? Well, notice because this larger figure is a square, these are all right angles, so these are all right triangles. And again, thinking back to one of our first questions, if you know two legs of a right triangle, you can use the Pythagorean theorem to calculate a missing side. Okay, so I'd like to know this side here, or this side up here, but I don't see an obvious way to get it. Okay, so at that point, it seems like I'm kind of stuck, right? I don't know how to get these missing sides to get a side of the square. I don't know how to get the area of this triangle, right? Again, if I knew this base, that would be a good path, but I don't know that. Okay, so where do I go from here? Well, it looks to me like these triangles going around, they look to be like the same triangle. Now, I don't want to make that assumption, but that can perhaps guide me in the right direction. I could think about, all right, well, what can I prove about these triangles? Is there any way I can prove that they're the same triangle? If I could, well, then if this triangle and this triangle were the same, then the long sides would have to be 10, the short sides would be 2. I'd know this length right here, and I'd be in good shape. Okay, so how can you prove that two triangles are the same? Well, let's start with what we know. They're both right triangles, so they share an angle. And they both have, the hypotenuse is equal for those two triangles, right? Because the hypotenuse of this triangle is part of the square, the hypotenuse of this triangle is another side of the square, so all the sides of a square have to be the same, so those two hypotenuses have to be the same. Okay, so then what would I need beyond that to show that the triangles as a whole are equal? Well, notice if I could prove that they share one more angle, then I'd be in good shape, right? So let's say I'll call this angle A here, right? So if I could show that angle A was equal to this angle right here, I'd be in good shape, because then I'd have angle, angle, side. Okay, two angles and a side mean that you have congruent triangles, or triangles that are the same. And just as a reminder, you've got a list of a bunch of different possible ways to show that two triangles are exactly the same. If they have two congruent angles and a congruent side, or all three congruent sides, or so on down that list. Okay, so that's one way to think about it. If I'm able to show that this angle A is equal to this angle, I could say that those two triangles are congruent. You could also think of it from the perspective of similar triangles, right? So if this triangle and this triangle share two angles, well, based on one of the questions we did earlier, we established that means you have similar triangles. And these two triangles also have the same hypotenuse. So they're similar triangles whose sides are in a ratio of 1 to 1. Well, that means all their sides are in a ratio of 1 to 1. In other words, they're the same triangle. Okay, so let's see, can I prove that these two angles are the same, or at least that they share an angle? All right, well, I'll just fill in some more unknowns here. Let's call that angle B. Okay, and we'll call this angle A, and this one here, I'll just call it X. And if I could show that A and X have the same measure, then I'd be in great shape. Okay, so what do I know about A and B? Well, remember, the angles in a triangle need to add up to 180. So A plus B plus 90 equals 180, so A plus B on its own got to be equal to 90. Okay, what do I know about B and X? Well, notice this here is a right triangle. That's a right angle because we have a square. And I also know along a straight line, if you add up all the angles along a straight line, those have to be equal to 180. So if I add B plus 90 plus X, that has to be equal to 180. Or in other words, B plus X has to be equal to 90. Or I'll write it this way, X plus B equals 90. Okay, so anything jumping out? A plus B is 90, X plus B is 90. Well, looking at that, I can see A and X have to be equal to each other. Okay, so if A is equal to X, all right, that means I'll just write A up here, Okay, so these triangles do in fact share an angle. So that leads me down the line of analysis. Well, angle, angle, side, those two triangles have to be congruent. They have to be the same triangle. So the long side of this one is 10, so the long side of this one is 10. Okay, the short side of this one is 2, so this short side is 2 up here. And that same logic I use to show that these two triangles are the same, I could just keep doing if I go all the way around, right? This triangle here has to be the same as this triangle, and so on. So I can just fill in 2 and 10 going all the way around. Short side of the triangles are 2, long sides are 10. Okay, so we should be in good shape now. We can get, if we wanted, one side of this square, it's equal to the hypotenuse, so I'll use my Pythagorean theorem. A squared plus b squared equals c squared. In this case, a and b are 2 and 10, so I get 104. Okay, so then that's c squared. C is equal to root 104. Okay, I could start breaking that down, but the only reason I wanted c was to find the area of the square, right? The area of the square is c squared, so the area of the square is root 104 squared, or 104. Okay, now might as well just calculate it the other way I mentioned. At this point I'm probably good to go, but just in case you're interested, we could think about, you could also find the shaded area by doing the area of the whole figure minus the unshaded. Well, the whole figure is a square with a side length of 12, so the big area, the area of the big square, is 144. The area of each of these triangles is 1/2 2 times 10. So the triangles each have an area of 10. And then I've got 4 of them, so altogether those triangles have an area of 40. So 144 minus 40, yeah, that's another way to get to the shaded area of 104. Okay, so what's left? Well, I have to compare 104 to 36 pi, so don't want to forget about the pi. Pi is a little bit bigger than 3. Well, what's 36 times 3? So it's 30 times 3 is 90, plus 18 is 108. So 36 pi is a little bit bigger than 108, so that's going to be bigger than 104. So that gives us the correct answer of A for this one. Okay, so any take-homes for this question? Well, circles and squares, squares and circles, that's a fairly, frequently tested topic. So good to know, when you have a circle inside of a square, you can kind of reason your way to the radius if you know a side length of the square. Now, what about for this question? Well, are you likely to see this exact diagram on your GRE? Not hugely likely. So what I take away is the general process that we followed, right? We thought about, okay, how do we get what we want? We want to find the side length of the square, or we want to prove that we want to find a way to calculate the area of those triangles. Okay, how do we get there? Well, if we could prove that these triangles were the same, that would lead us in the right direction. We could get the dimensions of those triangles, and then we'd be in good shape. So we did all of that, and again, that led us to the correct answer of A. All right, so that concludes our last question. All right, thanks so much for watching Geometry Part 1. I hope you found those questions and concepts helpful, and if you enjoyed the problems, feel free to check out the next video in the series, which will be Geometry Part 2. It's going to cover some of the same concepts, but apply them to more challenging problems. All right, thanks again for watching. I'll see you next time.